Hi everyone, my name is Piotr and I will, as always, talk about database drivers, how to use them, and even more importantly, how to not use them incorrectly. I also co-wrote some books and I encourage you to check them out. There's also a special P99 promo code, or more specifically, P992024 promo code for a nice discount. Drivers. Drivers are just a programmatic way to communicate with the database. Databases usually implement a protocol or multiple protocols to allow users to read and write data, modify database schemas, do some maintenance work, and whatever implements this protocol specification can be called a driver. The main idea behind them is to create an abstraction layer for users so that all the ugly details are hidden and the users can just ergonomically use the database to store and access data. On top of that, drivers can prevent users from anti-patterns, so using the protocol in an incorrect way. They can store additional logs, metrics, they can implement integrations with various observability tools. They are often coded in a few popular programming languages to make it as easy as possible to actually use a database in production in an efficient and correct way. Drivers don't have to be complicated, even for a custom binary protocol. And this slide, for instance, is also a quite functional driver you can use to insert rows into ScyllaDB and read them. It doesn't exactly have many features, but it kind of works. It sends requests to a database, it can receive a response. It's actually great at sending multiple requests concurrently. And still, normal users would expect a tiny bit more, like proper deserialization of results, handling timeouts, error handling, retries, topology awareness, caching, paging, and all that. For the sake of completeness, not all databases are client-server architecture. There's a whole family of embedded databases where the code for communicating with the database is the database. So you can say that the database is its own driver, and there's no protocol for sending and receiving messages. In this talk, however, we'll focus on clients and servers. Developing databases would be much easier if not for one very annoying aspect, which is database users. Database users and their database usually form a standard client-server relationship where users ask for things to be done and the database tries to serve all the requests. It's a quite complicated relationship where clients tend to assume that they have an exclusive deal and they just want to maximize their take, while the servers try to be the reasonable, thoughtful, and selfless ones, trying to make everyone else happy. Clients may be cooperative with their peers, but often they are not, and they would prefer to be the only exclusive users of the whole database system. And servers are most efficient when there's work to do and their queues are constantly nearly full with requests. They shouldn't be too full with requests though, because when servers are overloaded, clients' latency gets worse and worse since requests need to wait in line until the servers catch up and nobody's happy. User workloads can be interactive, batch, or anything in between on the spectrum. A great example of an interactive workload is users trying to access a web page. They appear out of the blue, send some relatively short requests, expect to get answers as fast as possible, ideally before their precious attention span window runs out, and then they are gone. You have as a database developer, little control of how many users are there. They may come in bursts when your web page ends up on the front page of Hacker News, and you can get totally zero traffic during night hours. Batch processing is different. It has a batch of things to process, for instance, terabytes of illegally spied user statistics, which then need to be filtered out, categorized, aggregated, and later used to optimize your shady advertisement platform. Those kinds of workloads don't care much about latency of a single request. They just want great throughput so that the processing takes a few hours and not a few days or a few months. Speaking of throughput, it's important to clarify what we're measuring here. The metrics we're actually interested in is goodput. And here's how you can distinguish one from the other. Throughput is a number of bytes you send over the wire. Your Ethernet cable that connects you to the world or your wireless router have some maximum throughput called bandwidth. And goodput, on the other hand, lives in the application layer. It's the amount of useful information you send. For instance, if you compress the data you're sending over, you're reducing throughput, but your goodput is really still the same. If you use HTTP to send your data, HTTP and TCP protocol headers count to your throughput, but not really your goodput. From the point of view of goodput, protocol layers are just pure overhead. In the database world, you also need to take into account if you ever need to retry a request, send some additional metadata like error message details, warnings, whatever else. That's all throughput. And even though your router metrics may show 20 megabytes per second, it's quite possible that you only squeeze 1 megabyte per second of actually useful data to the server or back. Maximizing goodput is good. Maximizing throughput may be good or bad. One other aspect of the complicated client-server relationship is timeouts. Sometimes it's the user code that times out and assumes that the request is lost or that the response is no longer relevant. And at other times, it's the server that decides that processing already took too long and just stops the execution. User-side timeouts are tricky because usually there are lots of users. Nobody really keeps track of them all, while there are only a few database servers to handle them all. The main issue is that once a user decides to give up waiting on a request to finish, the server usually doesn't have a clue that it happened and continues handling this request. The user might also decide that since the request failed or is no longer relevant, it needs to be retried, making the server-side queue even longer and more overloaded. There used to be a very nasty bug in the Cassandra Python driver, which worked as follows. First, request number 1 gets sent. Cassandra protocol has built-in concurrency mechanisms, so the driver just recorded that it is waiting for response number 1 and continued operating. Meanwhile, the request timed out on the user side only, and the driver just forgot about it. It then sent a new request, also assigned number 1 to it, which was kind of an early optimization to reuse the lowest available request number. Except this request number wasn't actually free for the taking, because it only timed out in the driver, while the database server still worked on it and eventually returned a response. And as a result, the newly sent request got a response from the old request number 1. It may sound harmless, because we just got a mismatched response, no big deal, except it's very much not harmless. If we now assume that these requests were log me in requests, and now we managed to log user B into an account owned by user A. That's not good, especially if user B is not a good person. That's why user-side timeouts are super tricky. The solution to this particular bug was to still keep track of timed out requests for a while in the driver so that it doesn't decide to reuse the request number too soon. But there's also a more general viable workaround, which I will mention in a few seconds. Server-side timeouts, they are not tricky. They are the exact opposite of tricky. The server just needs to make a hard decision sometimes, that it already spent too much time handling a particular request and the response is no longer relevant, so an error is returned to the user instead. Server-side timeouts are very useful for making sure that we don't have the kinds of bugs I explained on the previous slide. Namely, if you always make sure that server-side timeouts are shorter than user-side timeouts plus some estimated network latency, your life will be way easier. It just makes it more likely that if a request timed out in the driver, it also already timed out in the server anyway. There are usually a few ways of configuring server-side timeouts in databases. You can have a global timeout saying that the request should never take longer than a second. And then you can also have per query timeouts. Those make sense if for a specific query, you either want a response in, say, 100 milliseconds or not at all. Those kinds of short deadlines make sense in ad tech, hedge funds, trading bots, and other use cases like that. Drivers work best if they are smart. And in order to be smart, they need lots of useful information. Let's go over some examples. Topology. It's information where the database servers are, how physically far away from each other and the users. Some database systems, like DynamoDB, for instance, don't expose that information at all and instead give you a single comfy URL to send all the requests to. Other databases make the topology public in order to give drivers and users the opportunity to be more efficient. For instance, always contact the physically closest database server directly, which is hopefully best for your network latency. Topology information is by default always a little bit stale. If drivers want to keep it up to date, they need to constantly refresh it. And on the other hand, they should not refresh it too often because it's a throughput overhead. There are different ways of getting information about topology changes. Drivers can just keep asking the database if anything changed, or subscribe and wait until the database informs them that something changed. And in a distributed system, there's also an additional issue that each server can have its own idea on what is the current topology. So if you want to get consistent information, we either need to ask more than one server or rely on one of the consensus protocols like Raft or Paxos. Topology aside, there are also other kinds of useful information a driver can collect. For instance, statistics about how overloaded the servers are can help the whole cluster because drivers can consciously send requests to servers that are less loaded. On the other hand, if this information is not really up to date, users may think they are connecting to a server that has lots of capacity while it doesn't anymore. So it gets overloaded instead. A very tricky subject. Gathering some historical load can help with that because then you can try and estimate if the server is going to be busy soon or not. On top of the topology of your servers, it also makes sense for the drivers to know how far they are from the database. That includes things like being in the same region, same data center, or same rack. Now let's dive into caching. There are lots of things to cache in a distributed system to make it appear faster, but it can also ruin consistency guarantees if you go too far. A list of examples of things that you can cache in a driver: prepared statements, query results, topology, and schema information. Let's go over each of those in a little more detail. Lots of databases have a notion of prepared statements. A non-prepared statement is usually just a piece of text in a query language that the database understands. Once it arrives, it needs to be tokenized, parsed, and only then executed. That takes time. It's very repetitive work, especially if you constantly serve similar queries. So as an optimization, you can just save some pre-processed data about a particular statement and keep it cached in the database side. That's usually what a prepared statement is in a database system. Those prepared statements cost resources too, like database memory. So in order to not to run out of these resources, databases need to evict some prepared statements if there's too much to handle. There are many interesting algorithms of cache management, and databases usually implement a variant of least recently used or least frequently used. One important thing to be aware of is that you should only prepare statements that are going to be reused a lot. So in particular, if you need to send some initial queries on startup to register register yourself as a client or get some metadata, these kinds of internal queries are better not prepared, since they could push other hotter queries out of the database cache. Another thing that usually comes to mind first when talking about caching is just caching query results. There's an obvious upside to that with users getting data locally instead of making costly round trips. However, this is not the kind of caching that drivers should usually do. Caching makes users responsible for keeping the data consistent, and that's a very complicated topic in a distributed systems world. So if users want to cache anything and are sure it's okay to do so, then they should just cache it in their application, in the application layer. If this layer has more context, knows more about the data, how long it remains valid, and so on. Drivers should only do that if they are very, very careful about consistency guarantees. As for topology and schema information, that's always cached by default because it's information that can constantly change. Inside the driver, you can never really assume that you have latest up-to-date information. You can only hope that you're not too far behind. It should be a very conscious decision if you want to poll those changes often or maybe register and wait for them. And in some cases, it's also a valid approach for lightweight applications to just not store any information at all and just optimistically send queries hoping that they're match. Because, for instance, neither the topology or the schema is expected to change very often. Retries. Retries are one of the main benefits of using proper drivers to contact your database. Retrying creates an illusion that queries just work, even if sometimes underneath they actually didn't at first. On the other hand, misconfigured retry mechanisms may just as well suffocate the whole distributed system. When do we retry? On errors, usually. But not all errors qualify for a retry, and there's no single universal best strategy for all kinds of errors. Some of them make no sense to retry at all. If you send your query with a typo, then retrying won't magically make it correct. If your username and password is wrong, likely you just need to configure it out manually first. Other errors make perfect sense to retry. For instance, if your read failed because of a network hiccup. There are multiple strategies to deal with retries, depending if the database was kind enough to give us more context on what happened. For instance, if a node is overloaded, it's better to wait a little or retry with a different server rather than trying the same one again. And then another thing that not all queries qualify for being retried. If we don't know if the query failed, for instance, if we speculatively send another request in case the previous one timed out, we need to be sure that this request doesn't have side effects. Reads are generally fine to retry, and conditional statements are usually okay too. And if you try to create a table twice, one of the requests will succeed, the other will not. Usually no big deal. But if you increment some value in your database, you probably only want to do it once. And in that case, careless retries are pretty much out of the question. Some database drivers don't come with built-in retry support at all. And that simplifies the driver API, but makes life very complicated if users actually want to retry, because they need to implement their own retry logic. This is a very common source of errors, with the naive implementations not taking into account that queries may have side effects, or that sending a retry to an already overloaded server or sending a retry too fast just makes the situation worse. Summary of the most common retry policies is as follows. The most obvious one, which is also often the best for your good put, is not to retry. If the use case you have can survive that, great. If you do need to retry, sometimes it makes sense to retry contacting the same server again, for instance, if it's the closest one in the topological sense. And at other times, it's better to contact a different machine, for instance, if you're sure the previous one is overloaded. Then retrying immediately may start an avalanche and a retry storm, which can just kill your whole cluster. So it's usually better to wait a little to give your server some leeway to process the existing load. Then if you really care about getting a response on time, it may sometimes make sense to speculatively retry, even if the driver is not yet sure if the request failed or not. But in that case, only idempotent requests should ever be retried. Paging. Paging is a mechanism you need to implement in an incorrect way a couple of times until you can legally call yourself a database driver developer. The idea is deceptively simple. Results should be served in smaller bits so that you don't use too much memory on the server side as well as user side. Get decent latency, since the total result size can sometimes be gigabytes or terabytes and beyond for analytical data. Then it also makes it possible to pipeline the work, fetching the results asynchronously with users processing them at the same time. And paging also gives the users a chance to fine-tune the parameters so that it fits their use case better. Interactive workloads are usually better off with small pages constantly fed to them with low latency, while large analytical workloads can consume the results in larger batches because they generally prefer high throughput over low latency. The final big topic, concurrency. So multiple things being able to make progress at the same time. Concurrency just means ability to run things in parallel, everything happening at the same time. So instead of sending requests to your database one by one, always waiting for the previous one to finish before sending the next one, you just send them all, or at least a subset of them. Let the database figure out how to schedule them and wait for the results simultaneously. A natural source of concurrency for a database is users. Each user just does their own thing, but they send the request to the same database. So from each user's perspective, the database just serves their queries, but in reality, the database needs to figure out how to make every user as happy as possible. When concurrency of the input is high, the database has more things to do, which is good, because servers should be busy in order to be cost efficient. But if concurrency gets too high, it only increases latency for users. If you send 10,000 requests to a database, and it can only serve 1,000 requests per second, you will wait 10 seconds on average to get everything done. On the other hand, if you only send one request at a time, your database will likely not be able to reach full speed. That's because modern hardware, network cards, and VME drives all thrive in high concurrency environment. Let's say that your disk that you just bought has a shiny label on it that says up to 20 gigabytes per second read throughput. What the label doesn't say is that it will only happen if you read multiple things at a time from this piece of hardware. Otherwise, you just want to be able to physically saturate the bandwidth. Applications should take all that into account and give users tools to first of all allow concurrency and then configure it conveniently. That usually boils down to making sure that your driver exposes it an asynchronous interface, which most of the popular languages already have built in one way or the other. That's it. Thanks a lot.